this demonstration, we will use the new ZCU208 evaluation board to look at the RF performance of the latest generation of the RFSoC family. We'll use a RF loopback test to loop the Dacs back to the ADCs. So here is the 208 board. We're highlighting the actual RFSoC device here. It's in a socket in this particular board. This is the Gen 3 family. We're using an RF board. This breaks out the differential RF outputs and inputs for access. The ADC input side of the board. And also to highlight, we will be using the onboard DDR memory to generate both the test signal for the DAC and to capture the output from the ADC for analysis in some VSA software. The DACs and the ADCs, and indeed the whole board, is set up via some PC software, and the main interface is via this Ethernet connection here. We'll show some of the GUIs later. And one other item to highlight here are these differential clock inputs. So these clock inputs are used to either provide the RF sampling clock for the DACs and the ADCs, these high frequency gigahertz sampling clocks, or indeed they can be used to introduce a reference clock. So we'll start by bringing in a high frequency 8.8 gigahertz clock for the DAC, and half that frequency is used for the ADC for this test. So the ADC will sample at approximately 4.4 gigasamples per second. Just take a close look up of the external lineup. So we will connect DAC 0, which is generating our test signal, into ADC 0. We have a differential output that goes into a balun to convert it to single-ended. The single-ended signal goes through a bandpass filter, as highlighted here. And then the output of the bandpass filter is fed into a linear amplifier, and this is to compensate for some of the losses between the DAC and the ADC. So the output of the amplifier is then fed into another balun, and this balun converts the single-ended signal into a differential signal and into the differential inputs of the ADC, where it is sampled and stored in the DDR highlighted earlier for analysis. So here's the GUI. We're going to set up the DAC. So we set up the DAC to take in some baseband IQ samples from a file. We upconvert those to 4.9 gigahertz, as highlighted here. And we also have an interpolation factor of 6 running, as you can see on the GUI there as well. So once we set up the DAC digital upconverter, we can then read in some baseband IQ samples from a file. These samples are for 2 5G NR carriers, as you can see there, each 100 megahertz. So we're generating the signal on the DAC now, and we'll flip over to the ADC. And similarly, the ADC is capturing these 5G NR carriers centered at 4.9 gig. So they need to be down converted and shifted to baseband IQ. So we have a decimation factor there of 12 and a down conversion. And that's the captured output from the ADC. So you can see the 2 carriers there very clearly, a combined bandwidth of 200 megahertz, 2 100 NR carriers, and just some information there on the power of the received signal. And you can see the number of samples that we are acquiring and storing in the DDR memory. So once we've gathered those samples, as shown here, into the ADC, we can export that ADC data to an external tool, a Keysight VSA software actually. So we're going to just export the data from the GUI itself into the tool. And here you can see the 256 QAM modulation on the subcarriers. An excellent EVM there, 0.369% EVM. That's for the first carrier. We can also take a look at the second carrier now. Just we'll swap over here and grab the second carrier. Okay, just select carrier. And there again, we see 0.395. So again, excellent EVM being shown for the second carrier as well, as captured by the ADC. So one thing we can do now is we can use the on-chip PLLs. So what we'll do now, instead of using a high-frequency external sampling clock from the generator, we will bring in a reference clock. This reference clock is 491 megahertz. It will come from the generator, and we'll synthesize the clocks from the PLLs on the chip. So the configuration of the Dacs and ADCs is very similar. We're going to set up the DAC again. Only difference here is that the DAC is using the clock from the on-chip PLL to synthesize the high-frequency sampling clock at 8.8 gigasamples per second. And similarly, we will use the GUI to set up the ADC. Again, the ADC is using the PLL on the chip as well to synthesize its sampling clock of 4.4 gig. And again, we have to down convert and a decimation of 12. So we acquire the data. It looks the same as the last time. We can clearly see the two carriers and some information there on the power of the received signal and the number of samples we are taking. And yet again, we can take this data and export it out to Keysight VSA software. So here we see EVM of 5.8%, again 0.58% I should say. So again, excellent performance there. So again, this is the setup we used, a very simple demonstration using an RF loopback to show you the combined performance of the DAC and the ADC together. So synthesizing the signal in the DAC, looping it back through a filter and an amplifier into the ADC, and the combined EVM performance is what we've demonstrated in the Keysight VSA software tool. So again, 0.37% with the external RF clocks, 0.58% with the on-chip PLL, both excellent performance numbers shown there. And if you want to find out more information about the latest generation of RFSoC devices, you can go to xilinx.com/RFSoC. And to find out more about this board, you can go to /ZCU208. So thanks for watching.